Okay, today we're going to talk about absolute dating. So we're going to discuss the techniques that are used to figure out the precise date when a particular rock formation formed. And this is different than what we talked about last time, which was relative dating, where we're looking at the positions of different strata relative to one another and deciding which one had formed first and which one had formed later. But in this case, we're abandoning that order for actual precise dates when things were formed on the landscape. So in order to understand this concept, we need to review a little bit about the basics of chemistry and physics, and basically about how atoms work. So we talked about atoms back when we talked about minerals, but to review, an atom is basically the smallest unit of any element that still contains all the basic properties of that element. So all the elements on the periodic table have atoms that make them up, and this particular picture is of a carbon atom, one of the more common atoms near the Earth's surface. And the way that we define what an atom is by looking at the number of protons that the atom contains. So in the atom's nucleus, which is the center of the atom, which in this picture you can see is the area where the blue and the red circles are joined together, there should be protons, and there should also be other elements or other particles called neutrons there. So the protons have positive charges, the neutrons have neutral charges, and it's the number of protons that defines a particular element. So in this picture, we can only see 4 protons, but if we were to dig around behind this little gathering of subatomic particles, we would expect to find 2 more, because we know this is a carbon atom, and every single carbon atom on the planet has 6 protons. That's what makes it a carbon atom. So atoms can gain or lose other things. They can gain or lose neutrons, or they can gain or lose electrons, the negatively charged particles on the outside of the atom, and that will make them either an ion or an isotope, as we'll discuss in a minute. But again, if they are a particular element, such as carbon, they will have a very set number of protons that cannot change. So an isotope is, as we mentioned, a particular version of an atom that may contain a different number of neutrons. So while the number of protons in an atom, its atomic number, is very set, it's not something that can change, the number of neutrons may be able to increase or decrease, and so many atoms have different versions or different forms of that atom that can exist in nature with different numbers of neutrons. So for instance, carbon is most commonly found with 6 protons and 6 neutrons, and that gives it a weight of 12, 6 plus 6. But sometimes we also find carbon 13, which has 6 protons and 7 neutrons. And sometimes we also find carbon that has 6 protons and 8 neutrons, and that's called carbon 14, and that is a radioactive isotope. So that brings us to our next point, which is about radioactive isotopes. So certain isotopes, not all isotopes, have a property that we describe as radioactivity, and that means that these materials are inherently unstable, and because they're inherently unstable, they have the tendency to transform over time, and as they do that, they release energy in a variety of ways that can be potentially damaging to living organisms, to cells, and to other kinds of things in the environment. And so this breakdown process is described as radioactive decay, and it's easily tracked because, as we'll discuss more in a minute, as an atom experiences radioactive decay, it typically transforms into a completely different atom. So in the case that's shown on the diagram at the bottom of this slide, a carbon-14 radioactive isotope experiences radioactive decay, and it ends as a nitrogen atom. It has become a different element than the element it was in the beginning. And so in that way, it's easy to track when this process is taking place. So this radioactive decay process is important. It's a natural process that occurs around us in the environment all the time. We can track it because the original material that's called the parent nuclide or isotope is different than the thing that it transforms into, which is called the daughter nuclide or isotope. And so it's easy for geologists, relatively easy for geologists and other scientists to track how this process is taking place over time. And in particular, what we know is that the precise time that any particular particle is going to decay or experience this transformation is unknowable. That's what we would call stochastic. It's unpredictable. We can't know exactly when it's going to happen. But what is very helpful is that if we have a large group of radioactive isotopes all together, we can predict the rate at which a group of those elements or a portion of the group of those elements will have transformed. And we use a process that's called half-lives to describe the rate of this particular transformation. So what a half-life tells us is it tells us how long we would expect it to take for half of a group of radioactive isotopes to experience this decay process. So if we had 100,000 carbon-14 radioactive isotopes, we could expect that after one half-life had elapsed, half of those, or 50,000 of the carbon-14 radioactive isotopes, would have transformed into nitrogen, and the other half, about 50,000, would still remain in their original radioactive state. Okay, so each particular radioactive element has a specific length of time that its half-life covers. So, for instance, carbon-14 has a fairly short half-life, about 5,730 years. That's how long it would take half of a large group of carbon-14 isotopes to be transformed. Other elements have even longer half-lives. So uranium-235 transforms into lead, and it takes 710 million years for half of those radioactive uranium isotopes to transform. Potassium is another common thing that we observe transforming in nature, and it's used in geology to allow us to make predictions about dating. And potassium-40 transforms to argon-40 with a half-life of 1.3 billion years. So you can see that a lot of these half-lives occur over really long periods of time. At the top, there's a graph here that's showing the process of this half-life transformation. So you can see the parents are shown in the blue line and the daughters are shown in the red line. And you can see that at the beginning of time, when the radiometric clock starts, all of the materials we would expect to be parents. And then over time, we would expect that as the parents transform, they turn into daughters. And so as parents disappear, daughters increase. And after one half-life has elapsed, which we can see along the bottom of the chart here, there's about 50% of the materials that are parents and 50% are daughters, which makes sense. And then after that, after one more half-life has elapsed, about 50% of the atoms that started out as the parent at the beginning of that half-life, so at half-life 1, have transformed into daughters by the beginning of half-life 2. So the number of parents drops from 50% to 25%, right? It's divided in half over that time period, and all those additional parents that have disappeared have transformed into daughters. So that loss of 25% of the parents have been added to the daughters, and by the time the second half-life has elapsed, there's 75% of the material that is daughter, and you can continue on this pathway. So a graph is one easy way to, or maybe not easy, one way to kind of track how the population of atoms or isotopes may be transforming over time. I find it's a little bit easier to understand in a table. So here I have created a table for you, and this table basically tracks the same thing that we see in the graph over on the top left. So at the beginning, all of the materials are parents. The blue line is up high at 100. The red line is down low at 0, telling us that there are no daughters. After one half-life has elapsed, half of the materials have transformed into daughters. So there's only 50% of the parents left, and now 50% of the material is in a daughter state. After one more half-life has elapsed, we would divide 50%, the number that's in parents, by 2. So 50 divided by 2, half of 50 is 25. So there's 25% parents left, and then we would add all those to the daughters. So 50 plus 25 is 75. Then at the beginning of half-life 3, we would have only half the number of parents that we had started with one half-life before. So we would take 25% of the parents that we had at the beginning of half-life 2, divide that in half to get 12.5, and add all those additional elements to the daughters. So now the daughters have grown from 75 to 87.5%, and then you can continue to kind of follow the math down to fill out the rest of the table. So over time, parents are decreasing as daughters are increasing. All right, another way that we can think about this table is that we can try to understand the ratio between parents and daughters in a particular material. So for instance, if we had 3 times as many daughters of a particular substance, like argon 40, compared to potassium 40, then that would tell us that there was a particular ratio of daughters or parents, and we could try to match that ratio up with a particular point along the timeline that would tell us how many half-lives have elapsed. So if we look at this table, we can see that after 2 half-lives have elapsed, we have 75% of the material in daughters and 25% of the material in parents. And at that particular time, there's 3 times as many daughters as parents. And so if that was the ratio that we had seen between daughters and parents, then we can assume that at that particular time, 2 half-lives of the particular material, particular radioactive isotope that we're looking at, have progressed. Or maybe we are looking at a time where the amount of parents and daughters was equal. And so we would know that if the amount of parents and daughters were equal, that occurs after 1 half-life has elapsed. We can see that at that time there's 50% parents and 50% daughters. That represents a ratio of 1 to 1 between parents and daughters. And so we would know that that amount of half-lives have elapsed when that is the ratio that we find in the particular material. Okay, so this dates rocks from when they were formed from a melt. So when a particular igneous material transformed from a magma or a lava and became a rock. So as I just said, it's important to understand that the timestamp that the radiometric dating allows us to learn about particular materials doesn't tell us when every single type of rock formed. For instance, if we had a sandstone Many of the grains in that sand may be quite a bit older than when the grains of the sand became cemented together to form that sandstone formation. So maybe the sandstone itself is only 30 million years old, but it might contain a little grain of quartz that hasn't been remelted or transformed for over 1 billion years. And if we were looking to date that material and we pulled out that grain of quartz, the date that we would get for that quartz would be 1 billion years, which would tell us the date when that mineral formed, and it wouldn't be indicating the time when that mineral had joined together and been cemented together with the other materials. So if we're trying to learn the dates of layers that are not formed in an igneous manner, what we should do is we should look for other kinds of potentially igneous layers that might be contained within or around the other sedimentary layers to help us give context to when those sedimentary layers could have formed. For instance, if we had a sill or dike that was cutting through a particular layer, we know from relative dating that that dike must be younger than the material that it intruded into. And so we can date that dike, like in this diagram, that formation D to a potential age, maybe 50 million years old. Then we could know that for sure that layer A of sandstone, or B, perhaps that's a limestone below it, those layers must be older than 50 million years old because they must have been around at the time when the dike that we can see in the diagram here labeled as D formed. All right, so that is going to conclude our discussion about absolute dating today. You guys are going to have an exercise that you guys are going to do that's going to help you think through the process of how this actually works when thinking about geologic material.